So thank you for joining us. My name is Lucy Wu. I'm the chair of the Young Members Presidential Group, the YMPG, a board level committee of the ISSMGE. And we have over 700 participants who signed up for this session. Here's a map of where everyone is from. And before we get started with our talks, we have a short introduction for the event. Welcome from the ISSMG board. In this session, we're focusing on adaptation to climate change. In recent years, I think everyone here has experienced the effects of climate change, from smoky skies, from forest fires, hotter climates, persistent droughts, and then on the other extreme, some of us have been impacted by floods from large rainfall, hurricanes, typhoons, cyclones, and of course, rising sea levels. So to start us off, we have Professor Andrew Whittle, who will give an overview of what adapting to climate change means for our profession. Then we have Sam Allen representing the International Geosynthetic Society, one of our sister societies, to talk about geosynthetics and sustainability. For those of you who attended our earlier session on mitigation of climate change, his talk will present a solution that reduces carbon emissions in construction and provide a way to face the challenges that our next speakers will touch on. Dr. Christopher Stevens from SRK will present a perspective from his work on building on permafrost in Alaska and cold regions. Dr. Robert Maliva from WSP will talk about the effects of sea level rise on groundwater in coastal regions. And last but not least, we'll end this session with a discussion on how we can adapt our careers to this changing climate with Dr. Jan Krupek from Araucan. So the purpose of this event is to inspire you to think beyond your borders, because our actions will contribute to these global issues and challenges. We are all connected. The topics we have chosen for these events are not your traditional geotechnical topics. We think that our profession is an integral part of the world around us, and to stay relevant, we need to actively engage with other engineering disciplines, the scientific community, urban planners, policymakers. We're here to challenge you to think beyond your borders, geographical, political, technical. These sessions are meant to enable you to continue the conversation with your colleagues and community. This is just the start. The next 40 years will look very different from the past 40 years. The challenges will be different. The skills that we need to solve these problems will be different. So we're here to invite you to help us imagine what our profession will look like in 40 years' time. So engage with us, make use of the chat, introduce yourselves, engage with your fellow participants, ask each other questions. The chat is here for you. If you have questions for speakers, please put them in the Q&A. There's no dedicated live Q&A session for this event, so our speakers will try to answer any questions you might have in the Q&A text itself. These sessions are being recorded and will be available for viewing about a month after this event, and you'll find the links through email communications. And I'd also like to introduce my co-hosts, Mario and Ash. Would you like to say a few words about yourself, Mario?
Of course, Lucy, thank you very much. You're welcome, everybody. We have been planning this event for a couple of months already, under the guidance of Lucy. So I think we are a bit tight of time, so thank you very much for participating again. And the idea of this event is to spread the word, to make our society bigger, and to think together about the future. So enjoy the sessions, and I will be back in a couple of minutes.
Ash?
Yeah, kia ora koutou. Just echoing the words of Lucy and Mario. Welcome to the sessions. I really hope you get something out of them. And yes, they're not the conventional geotechnical or geotech related talks that you might go to. So prick your ears up, and I definitely hope you get something out of it. Enjoy.
Okay, thank you. And now we have Professor Charles Ng, the president of the ISSMG, to say a few words about the society. Charles?
Yeah, will you please let me share the screen? Thank you. Right. May I get started? Thank you, Lucy, for your kind invitation for me to give a very brief introduction of the International Society for Soil Mechanics and Geotechnical Engineering. And in short, is ISSMGE. And just in case you are not familiar with the ISSMGE, and let me just quickly walk through with you. And the society was established in 1936 by Professor Kaltasaki and was formalized by Professor Skempton in London in 1957 after the Second World War. And up to now, we have 92 member societies and over 21,000 individual members. And I believe this is the largest geo-related societies in the world. So here is a list of the presidents, and you can see on the left-hand side begins with Professor Kaltasaki, Skempton, followed by Casagrande, Biron, Pear, and so on. On the right are the later presidents, and I'm the 17th president from Hong Kong. And then those are the dots represent the locations of the presidents. And now we are calling for the nomination of the next president. And if you do know anybody you think they are suitable, please through your member society to nominate the suitable candidates and to our Secretary General and Professor Neil Taylor. And just by the way, because the COVID and my term of presidency actually extended to May next year. Actually, I'm supposed to finish the term and this month, last month, but we cannot organize any council meeting, so that's why we have to postpone my presidency. And that also include the 12 board members, also their terms, and actually also extended to May 2022. And here are the pictures of 12 board members. In the interest time, I will not read them, and I'm sure you can see the pictures and also their name just underneath each picture. And this is the very brief governing structure of our society. And the ISSMGE board is responsible to the council, and the board is to drive and direct the function of our society. And we have 6 board level committees. You can see, let me just quickly walk through with you. And the first one on the left is Young Members Presidential Group. And as you can see here, actually, as you know, and chaired by Lucy Wu. And then we have a Corporate Associate Presidential Group. Now we have 42 corporate associates. And then we have Innovation and Development Committee and Technical Oversight Committee, and chaired by Professor Pierre Delage. And we have, up to now today, we have 35 technical committees. And we have Professional Image Committee. We also have Awards Committee. And I don't know whether you know, we have a bi-monthly ISMG bulletin, and the editor-in-chief is Anthony Leung. And this picture was taken when I was elected as president in September 2017. Really, time flies. At the time, I promised our society to focus on 3 aspects: education, innovation, and diversity. And by the way, let me just show you, actually Lucy's here. And if you notice, okay, standing next to Pierre Delarge. And so let me just quickly report to you 2 items what I have done for you. The first one I'd like to report is the virtual university. And what do I mean by that? Okay, virtual university consists of 3 major components: online postgraduate courses, online library, and also the publisher, online publisher. And up to today, we have established, you can see from the screen here, we have established 10 courses targeting postgraduate students and young engineers. And they are all free of charge. And those courses actually delivered by well-known professors and also engineers. And given the current COVID pandemic, and it has been proven actually very useful for many countries and also companies. As you know, many cities are locked down, so they can go to our website and use our postgraduate online courses to educate themselves. And also, I believe the courses also very useful for some company as well. Regarding online library, actually following the initiation of immediate past president, Professor Roger Frank, and I expand the online library to cover almost all ISMG related conferences and publications, online lectures, videos, etc. And third one actually is the publisher. What does that mean? That means if anyone want to organize a conference or symposium, can use our platform, and this enable the organizer to conduct the peer review process, and once the papers are accepted, they can be directly uploaded to our online library. And more features are being added to this publisher. For example, indexing and the DOI. And now, if I may invite you, okay, since today's event is the future of geotechnics, so may I invite you to imagine, okay, 20 years later, what would you like this virtual university to be? I just share with you what I think, okay? Whether you agree or even you can think even more beyond this, and I believe it should have it should be further enhanced, like open access platform, like the MOOC platform, should have homework functionality, examination functionality, credit functionality, and even degree functionality. And I believe the sky is the limit. Now, in addition to, and I hope you agree, this virtual university is a very excellent vehicle to promote geotechnics around the world. Okay, and this virtual university is free of charge, so to anybody, whether you are a member of ISSJV or not. Okay, and that I think that can permeate to every corner of the globe. And in addition to virtual university, we also have an ISSMG foundation provides a travel grant for young professionals or students to attend conferences. And also we have our own journal, International Journal of Geoengineering Case History, which is an online open access journal. And we also have a GeoWorld educator for geo-professional community. Okay? And you can find fellow geo professionals and interact with them. And also since on the bottom right corner here, since 2018, I worked together with Lucy and her committee, and I created the Bright Spot Lectures to provide opportunity for young members to deliver keynotes in plenary sessions, in international conferences or symposia, not in a parallel session. So we require the organizer to provide the opportunity, not less than 20 minutes for Bright Spot lecturers to deliver their keynotes. And let me just, so here just a couple of pictures taken, and when I give the certificates to those winners of the Bright Spot lectureship. And I believe actually Mary also one of the Bright Spot lecturers, if I remember correctly. And finally, and I would like to just introduce our sort of probably the most important conference of our society is the International Conference on Soil Mechanics and Geotechnical Engineering. And this conference usually is held every 4 years. But because of the COVID-19, and now the conference is rescheduled to be held in May 2022. And it is going to be conducted and using a so-called hybrid mode or a mixed mode. Then in addition to the main conference, actually there will be a International Young Geotechnical Engineering Conference, sometimes one parallel, sometimes one back-to-back. And also, we do under the ISSMG, we do have the regional conferences. Again, also held every 4 years in between the International Conference on Soil Mechanics and Geotechnical Engineering. And those 5 conferences include Australia, New Zealand, African, European, Asian, and Pan American conference. And that's all my about my short introduction. And may I wish you all well and healthy and enjoy this event. Thank you for listening.
Okay, thank you, Charles. So YMPG represents the voice of younger engineers to the ISSMG board, and being invited to the ISSMG board meetings, we have an actual seat at the table where decisions on the objectives, priorities, and goals of the society are being determined. So I'm going to share the results of the poll that we just took with all of you on Zoom and also on the screen for those of you joining us on YouTube. So you can see we have a variety of participants from all over. It's great that most of you have heard of the ISSMG before. But yeah, this session was timed to target for the North and South American audiences. And now please enjoy the event. So remember to put your questions in the Q&A, and then the answers will also appear in the Q&A, and please make use of the chat to say hello and things like that. And now it is my pleasure to introduce our first speaker, Professor Andrew Whittle. Professor Whittle is a professor of civil and environmental engineering at the Massachusetts Institute of Technology, MIT. His research deals with modeling soil behavior and predicting the performance of foundations and underground construction projects. His research has been widely used in major projects around the world. Professor Whittle?
Hello, you're waiting for me. Can I share the screen?
Yes.
Is that all visible and am I audible to everyone?
Yep, good to go.
Okay, well, first of all, thank you to the YMPG for inviting me here this evening. I've been given the unenviable task of talking about a very large topic in a very short space of time. So I was asked to talk about geotechnics and adaptation to climate change. It's helpful to have a framework to understand climate change, and this is as good as I could find in a single slide. You'll see that climate change begins with a discussion of the drivers of climate change, which revolve around the production of greenhouse gases, which are trapped in the atmosphere and increase air temperatures, and leads to a variety of climate change phenomena. Everything from sea surface temperatures and sea level rise to changes in precipitation patterns, extreme events such as droughts and floods. And in essence, these factors are causing adaptation of the human and natural systems. And as a consequence of this, we're having to consider different socio-economical development paths to handle climate change. And to cut this down to something really short and sweet, I would say that mitigation is basically controlling global temperature through reductions in greenhouse gas emissions. So that's that particular bottom pathway. And for geotechnical engineers, I think the adaptation part really relates to the policies and actions to reduce vulnerability and impacts on human populations. And I say this because there are, if you read the boxes, you'll realize there are other issues of ecology and so on that fall perhaps outside of what geotechnical engineers are involved in. And I was asked primarily to talk about the adaptation, but I should say that geotechnical engineers are involved at many different parts of dealing with climate change. In fact, I could say some of the most substantial ones relate to the role in mitigating problems. For example, in renewable energy, wind energy is a huge resource in the US. This is showing wind fields across the continental US and the coastal US. And you'll see that the wind fields shown here at 80 meters at the height of a wind turbine tower are particularly strong in the middle of the country and along the coasts. We already have a very well-developed wind industry. If you live anywhere from Texas up to Kansas, you know this. There are wind turbines everywhere. In fact, North America, or the US in particular, has 100 gigawatts of installed turbine capacity. But offshore, we've yet to start. Offshore, we're talking about individual turbines with capacities of 15 megawatts. These are absolutely enormous structures with rotor diameters somewhere exceeding 240 meters, and with the hub maybe as much as 150 meters above the sea level. And you can see a little picture, an illustration of the latest one from the International Energy Agency on the left here. What interests us geotechnically is that almost 30% of the capital costs of offshore wind are in the substructure. So optimizing the substructure has become enormously important. The North Sea in Europe has become the sort of epicenter of offshore wind development, but nearly all of it has occurred in very shallow water conditions, typically in the order of 30 plus meters, and involve fixed bottom structures. You'll see that of the North Sea installations, nearly all of them are fixed bottom structures, mainly with monopiles. But if we want to exploit offshore wind in the US, we're going to be in deeper water, and we're going to be in very different geological conditions, and we're going to have to deal with floating structures which are anchored. And there are now many projects proposing major offshore wind, and I'm sure many of you in the US and North America will become involved in these offshore wind projects running all the way from the Massachusetts coast down to North Carolina. Geotechnical engineers have also been heavily involved in another part of mitigation, which is using shallow geothermal potential to help with heating and cooling of buildings. As you're aware, the ground doesn't respond exactly to air temperatures. And in fact, there is a gradient of about 10 meters, where seasonal changes in air temperature affect the temperature in the ground. Below that depth, the temperature in the ground remains almost constant. And this has enabled people to use the ground as ballast or thermal ballast. So for example, ground source heat pumps enable seasonal heat storage. So in the summer, you have reject heat, you have excess heat in your buildings, you can store it in the ground. In the winter, you need to extract heat from the ground to heat the buildings. So you have a cyclic phenomena. Now, this has been around since the Second World War, ground source heat pumps, but the geotechnical community have turned this into something much more massive for larger scale applications. So you see on the bottom there, the use of geothermal piles or heat exchanger piles, where you combine the foundation response with the thermal heat exchange. So you can use the soil underneath the building not only as a foundation, but also as a means of heating and cooling, or assisting in the heating and cooling of buildings. People have even incorporated these things into linings of tunnels. So there's a lot of potential for underground infrastructure to help in mitigating some of the effects of climate change through heating and cooling of buildings. And in fact, you could turn this even further and say, we could use other underground resources. For example, abandoned mines would be a very good heat exchanger. But I was asked to talk about adaptation. And most discussions of adaptation begin with some of the obvious observations of climate change. Perhaps the most notable is global mean sea level. And this figure shows the history and projections of sea level rise. You'll realize that we only have about 25 years of accurate data around the world from satellites. And prior to that, we were relying primarily on tide gauges. This figure shows global sea level relative to 2000. And you'll see in the dark black line what we've actually measured. It's a rather unimpressive result so far. But you can see the projection going forward in time to the end of the century is heavily contingent on the way we develop socially, economically. The RCP are the representative concentration pathways. The red represents business as usual, and you can see has a very large uncertainty by the time we reach the end of the century. And the green is where we go towards zero net carbon zero in the next 20 to 30 years. And you'll see there's a huge range of uncertainty in sea level rise associated with these things, particularly in phenomena such as melting of Antarctic ice sheets. Geotechnical engineers are also familiar with the idea that it's not just sea level that we should be interested in. We also should be aware of subsidence. I was involved after Hurricane Katrina, and when you look at southern Louisiana, you realize there's a massive loss of land due to coastal erosion. Some of this is just simply due to subsidence of the land, natural subsidence in the area of the Mississippi, lower Mississippi Valley and Mississippi Delta. The figure on the bottom was a study done just after Hurricane Katrina and shows that the whole area of Greater New Orleans was subsiding anywhere in the range of 5 to 10 millimeters a year. That's about a centimeter a year. So there's a massive subsidence naturally occurring in the geological deposits. The figure on the top right shows you that many cities, especially coastal cities in Asia, have experienced much more subsidence than that. You can see the scale here is in the order of meters. Tokyo, for example, subsided more than 4 meters between 1900 and 1970 due to groundwater pumping. And if you look at these charts, you'll see that most of the cities in this figure have brought this problem under control, but they still use groundwater resources as water resource for the city. And the champion today is Jakarta. The figure is on the bottom right shows recent estimates of the settlement rates in Jakarta, and much of downtown Jakarta is settling 10 to 20 centimeters a year. So this is far larger than the 3 millimeters of global sea level rise. So we realize that some problems we're dealing with are man-made, and sometimes they're in collision with the natural world. What does all this lead to? Well, subsidence and sea level rise are creating conditions where storms are having more and more damage. This is a plot showing insured losses over the last, since 1970 to 2018. And the light blue color are coastal storms. They're by far the most expensive hazard. And you'll realize that the numbers there refer to the big hurricane events, which have swept through principally through the North Atlantic and the Gulf of Mexico. They're the most expensive hazard. By 2050, with projected sea level rise, we're expecting something like $1 trillion per year of annualized losses in the major urban conurbations on the coast. So this is an extremely difficult, large-scale problem. And it's caused, of course, by storm surge and extreme precipitation. Some people are climate skeptics, but the figure on the right should dispel your skepticism. This is the relationship between storm intensity, measured in red or shown in red, and sea surface temperature in the equatorial regions of the Atlantic Ocean. And you'll see the very good correlation here, showing how as the sea surface temperature, driven by climate change, increases storm intensity. And this is a figure which has made my MIT colleague Kerry Emanuel very famous, because it really translates into what we're seeing in storms. So climate change is going to increase the frequency and intensity of storms in addition to sea level rise. To give you some illustrations, what do I mean by this? Well, the figure on the left is showing the probability of achieving a storm surge greater than 2 meters, shown the day before Hurricane Sandy hit the North American coast. And you can see on the October 28th, there was a greater than 50% probability of a storm surge, a sea level rise greater than 2 meters. A day later, the actual storm surge was 4.3 meters and overtopped the flood walls at the tip of Manhattan Island. This was a major storm intensification, and we had very little forewarning of it. So it's a major hazard. A somewhat different story of intensification is Hurricane Harvey from 2017. This hit the Houston area, and the storm moved through incredibly slowly with very massive precipitation, the order of 48 plus inches of rainfall in the storm event. Here, the aging stormwater infrastructure couldn't handle the precipitation. Urbanization meant, without zoning, meant that in fact there wasn't a very an infiltration capacity to absorb this, and the ground was already saturated, so there was limited infiltration capacity. So coastal adaptation really is the biggest single challenge we face, and it requires solutions that address both storm surge and extreme precipitation. And I should say one of the biggest challenges for us in the US is the current regulations decouple responsibility for those two aspects of the problem, which is an interesting problem in its own right. If you're a hydrologist, you keep track of where the water comes and where the water goes. This is a little schematic, and it suggests the difference between a natural and an urban environment. And you'll see in the natural environment, with a heavy rainfall, about 50% of the rainfall may infiltrate into the underlying soil. In an urbanized environment, that might be as little as 10 or 15%. And with the same amounts or similar amounts of evaporation, you'll realize there's a huge difference in the amount of runoff, which has to be handled by stormwater systems. Up until relatively recently, major cities were tackling this by very large underground infrastructures. For example, in Tokyo, they built this absolutely enormous flood tunnel to handle extreme precipitation events. You get a sense of the scale by the people walking around. In many parts of North America, we're trying to handle these problems using green infrastructures. And I would say in general, there's been a major transition away from capital-intensive gray infrastructures, such as combined sewer outfalls, towards green systems which promote infiltration. And this has been true in New York City and Philadelphia, and to various degrees in other US cities. I'd say less so in Boston, in fact. So it's interesting because one of the questions is how effective these green infrastructures are. And my colleague Trish Culligan, who I worked with on a paper looking at this issue, has done a lot to evaluate and quantify these features. When we turn back to the coastal adaptation, you see a whole smorgasbord of things that have to go together to deal with that adaptation on the coast. And if you absorb the figures on the top, you'll realize there are a mixture of different strategies we can deploy on the coast. We can advance, for example, through land reclamation. Large-scale land reclamation is a feature of some cities such as Boston, which was done maybe in the last 100, 200 years. It's also a strategy of a place like Singapore, which has greatly increased its land mass. So advancing through land reclamation can be a part of a solution to adaptation, providing more land between you and the sea. You can famously look at protection systems, and protection systems fall into mixtures of gray and green infrastructures. The gray infrastructures are principally barriers and gates, levees and walls. These all serve to repel the water, but they don't attenuate the actions of waves. So we need to combine them with natural and nature-based features, which are illustrated in the figure on the top. But the challenge with these features is we often don't understand very well how effective they are, how to quantify their effects. Oops. And you can see the alternatives to this are accommodation, elevating structures, upgrading stormwater, or retreating from the coast. And there's a real challenge to try and figure out strategically in different parts of the world which solution is most appropriate or which combinations of solutions are appropriate. From a geotechnical side, the gray infrastructure is better defined and better designed than the green infrastructure. But frankly, it's the green infrastructure which is going to enable long-term performance of the gray infrastructure. So you can't cut one from the other. And geotechnical engineers need to adapt themselves to this more multifaceted world. We kind of already know what happens when you get a major flood event in a large city. Lower Manhattan was swamped in Hurricane Sandy, and the damage costs were more than 70 billion. Of that, about 25 to 30% were associated with infrastructure damage. And in fact, some of the tunnel repairs are still in progress. The figure on the left actually shows how much of the subway system was flooded 7 days after Hurricane Sandy. So we know that tunnels flooded with seawater don't respond very well. So what's the options for New York? What does New York face in the future? Well, climate change for New York City by 2100, we expect to see a sea level rise anywhere from 0.5 to 1.5 meters. And storm surge events, the 100-year storm surge event, is also likely to increase that by another 0.7 to 1.2 meters. If you combine these effects and you say we want to provide a protection, then for a return period of a 1 in 100-year storm, by 2100, that's going to be a 1 in 20-year storm. So in essence, the risks are going up over time with the sea level rise and storm surge. Already for New York, people are asking what kinds of infrastructure would be needed to protect the city. And as you can see from the map, a very large area is affected by these sea level changes. And the proposed solution that the US Army Corps of Engineers is coming up with, or one of them, involves barrier structures, large barrier structures and large gate structures. The figure there is a rendition of the structure for the Verrazano Narrows, the biggest of the openings. If you look at this project, this particular project, you realize we're talking serious money. This is $34 billion worth of infrastructure and could take 20 years to construct. So the lead time on this is really enormous. We can't just build this thing in a short space of time. And you've got to ask yourself tactically, given the uncertainties in climate change predictions, how do we proceed to reduce risk while maintaining some flexibility in design? In other words, is this an all or nothing proposition? Do we have to put our money down for such large projects now on the prospect of sea level change occurring? Much of that sea level change is already committed by our prior state of climate. Extreme rainfall also affects other things, particularly landslides. And if you go around the globe and you say, how is climate change affecting slope stability? There have been very few surveys of this. One which I found fascinating simply surveyed the different types of landslide and how it might be affected by changes in rainfall conditions or extreme rainfall events. The map on the top right gives the primary message. We can expect landslide hazards to increase almost everywhere across the globe. Annual mean precipitation is also a feature of climate change. And we can see the brown colors shows areas where there's going to be less mean precipitation. So you can see there are large chunks of the globe, particularly in the Mediterranean region, the southern parts or the equatorial parts of Mexico, the United States, and South America, where we're going to see extreme drought events, we're going to see much less precipitation. This is coming from the IPCC. How does changes in mean precipitation and general climate affect us? Well, many of the structures that geotechnical engineers are involved in are earth structures. And suddenly the whole issue of earth structure atmosphere interactions becomes a huge issue. This actually is an area of where research in geotechnical engineering has made a big difference. We've seen a huge advance in understanding partially saturated soils over the last 20 to 30 years. And there are two very nice ranking lectures, Blight and Jens, which describe the problems of earth structure atmosphere interactions. So we know now a lot about what will happen in a changing climate. If there's extreme droughts and desiccation, we understand the phenomena that will occur. But from an adaptation point of view, we now have to think much more seriously about how you improve the performance of earth structures, improved erosion resistance, improved durability. How do you stabilize fill materials? And what is the role of vegetation? These are questions that are largely open when it comes to general design principles. A later speaker in this session is going to talk about groundwater. Groundwater is a major source of drinking water in the US. About 38% of all our drinking water comes from groundwater aquifers and 43% of agricultural irrigation. These charts show the historic record of depletion of aquifers, and you see how the use of aquifer water between 1900 and 2000, over a 100-year period, compares to the period 2001 to 2008. And you can see that we are depleting nearly all of our major aquifers, particularly in the lower Mississippi and the Ogallala. And these are areas which are going to be big problems for us in the future as we cause all kinds of subsidence issues. Geotechnical engineers these days are often involved in assessments of aquifer storage. For example, in the San Joaquin Valley, in 2015 to 2017 in the drought, what you're seeing in the figure on the left are satellite images spotting ground surface subsidence due to lack of precipitation in that 3-year window. And they show rather clearly the magnitudes and the velocities there. You can see 20 centimeters of subsidence per year in that period. Of course, ground surface settlement is not just due to the withdrawal of water, but we can analyze volumes of water using gravity measurements. So these figures illustrate for you the range of remote sensing. And remote sensing, I think, is playing an increasingly large role in many of our geotechnical applications today. And you can see this by the study here involved with aquifers. So I forecast that there's going to be a lot of climate groundwater models trying to understand the interaction between soils, groundwater systems, and the atmosphere driven by future climate change. So those primary figures before were showing the historical record. People are now starting to forecast what happens to our aquifer systems going forward over the next 50 to 100 years. And what's interesting about these initial studies, and I think this is what this is, it's an initial study, you will see some aquifer systems, for example, 2, where climate change is going to cause further deterioration and create all kinds of problems, needing adaptation to address this. In other areas, you'll see in Northwest India and other parts, you'll see actually the reverse. So there are global winners and losers in the aquifer business. Finally, I thought I'd just say a few general words about climate change in the Arctic. In the Arctic, of course, we have permafrost conditions. We have permanently frozen ground, which is continuous or sporadic or discontinuous, as you can see from the map, covering the whole area around the Arctic. Arctic warming is occurring about twice as fast as global temperature change. The area, of course, is sparsely populated, and the most obvious observation is we're seeing a decrease in sea ice reductions. I can tell you, if you're interested in infrastructures, there's going to be many economic opportunities as global shipping moves towards the Arctic. So there's going to be new ports in the Arctic and all kinds of interesting things. But the most important thing, I think, relating back to climate change, is that as we warm this ground, all of the existing infrastructure is affected. So you can see that thawing of permafrost, and I know one of the latest speakers is going to talk about this, causes breakdown and damage to the coastal environment. It accelerates the erosion of coastal environments, and it damages everything in the way of infrastructure built through the Arctic. And the bottom figure on the right is, for me, is the TransAlaska Pipeline, which was built when I started my career. And you can see how they were already trying to insulate or isolate the pipeline from thawing of permafrost. A recent study shows us that a very large fraction of infrastructure in the Arctic is going to be affected by the thawing permafrost. So we can forecast geotechnical engineers dealing with many problems similar to the TransAlaska Pipeline of how do you isolate and protect infrastructures in the Arctic, plus whole new development opportunities. And finally, I should say that the permafrost itself holds some of the largest terrestrial supplies of carbon, organic carbon in soil. And the consequence of warming is that the soil organic carbon can be released back into the atmosphere. So thawing of the permafrost itself is going to create another problem. It's going to become a source of carbon or greenhouse gases, methane in particular, coming back into the atmosphere. So anthropogenic warming of the thawing permafrost is going to create a whole lot of other challenges. And you can forecast scientifically that there may be some plant growth in the thawing areas, but generally we can anticipate that there's going to be a lot of need to mitigate these effects. So we can see that geotechnical engineers may be involved in some of these very large scale problems. So the permafrost carbon feedback is going to become one of the biggest problems over the next 50 years. So that's my general survey. And I'd just like to thank you all for your attention and leave you with one message which should resonate with all the young people. It's unleash your natural curiosity. Remain curious, remain open to new ideas, and you will find solutions to some of these really interesting problems presented by climate change. And finally, I know Lucy wants me to wrap. I was just going to say, I apologize, I won't be here for the question and answer session at the end, but if you've got questions or comments, my email address is at the bottom there, and I'll happily answer questions afterwards. Thank you all.
Thank you. That was very informative. I am going to launch another poll. This is a pretty quiet audience today. And then with that, I'd like to introduce our next speaker, Mr. Sam Allen. All right, let me spotlight your video. So I'm very excited to introduce our next speaker, Mr. Sam Allen. Mr. Allen represents the International Geosynthetic Society, one of our sister societies. He's the communication chairs for the IGS. We're always looking for opportunities to collaborate across professional societies, so this is fantastic. Sam is a vice president and director for TRI's Environmental Group, a series of global laboratories providing routine geosynthetics verification testing, as well as sponsor research and development. So if you've joined us for our previous session on mitigation of climate change, you would have seen that the construction industry contributes to 6.4% of the direct global greenhouse gas emissions. Geosynthetics is one way to reduce this amount. So now I'm gonna end the poll, share the results, and turn the floor over to Sam.
Okay, thank you very much, Lucy. I'm assuming everybody can see my first slide there. Give me a thumbs up for that. Okay, and you can hear me okay. Well, very good. I'm honored to be part of this group. As Lucy referenced, the International Geosynthetic Society is a sister of your organization. We have many common denominator members, and we're very active in this response to the changing climate. What I'd like to do today is I would like to share with you a little bit about the IGS, the International Geosynthetic Society, some fundamentals about geosynthetics, and then kind of go directly into some of their contributions to sustainable infrastructure development. Dr. Whittle's presentation really wrapping up all of those things and the need to reduce the carbon footprint, to reduce emissions is certainly wrapped up and summarizes many of the more strategic applications of geosynthetics. and then I will conclude. The IGS was founded in 1983. We are dedicated to the scientific engineering development of geosynthetics, and our mission is certainly to promote their appropriate use, not only from the development of products and design of applications, the proper design of applications, the proper application of quality assurance in those applications throughout the world, but specifically and certainly most recently and urgently directed towards sustainable development, resilient infrastructure using geosynthetics. We have membership like you do all over the world, 47 different chapters, largely devoted to an individual country, but many regional. I'm, for example, part of the North American Geosynthetic Society that includes the United States and Canada. We have 2,500 individual members, a lot of student members, and many corporate members that help the society project the benefit of geosynthetics use. We are published extensively in 2 key technical journals, Geotextiles and Geomembranes, and Geosynthetics International. They're published quite well, 6 times per year. The impact factors, which are general matrix of how important they are, how well read, how applied they are, is very high for both journals, and that's good news for the journals. We have an active website, geosyntheticsociety.org. You can find out about our conferences there. There's a very active calendar, updated calendar section. We have a sustainability page. We have a digital library, many things associated with the website. And members use this and will be using this increasingly with a redesigned website to be released in about a month and a half to interact with each other. Chapter good and bad and ugly exchanges all over the world, so we can learn from each other in a much more efficient way. You can follow us on LinkedIn. You can follow us on Facebook. A lot of the efforts we have in terms of education and events and online webinars, all of those things are published heavily on social media. So as Dr. Whittle did a wonderful job sort of setting the table here, we humans have activities that are causing, making a contribution to global warming. And the rate of change is increasing. And if we continue to increase at the current rate, we are into some dramatic changes, not only in water rise, sea level rise, and elevated temperature, but also social changes as human beings migrate to better environments. All of those things are very important to the future. The very important aspects of this reach to the sustainable aspects of our infrastructure, reshaping goals for that infrastructure as they directly relate to societal development, with awareness of climate change and energy, natural resource protection, water, aggregate, those kinds of resources are in limited supply. How do we take care of them? And then certainly sustainable consumption, sustainable cities, sustainable practices. Some climate change is already here. It's inevitable. How do we accommodate that? How do we engineer and design for that? The United Nations came out with 17 sustainable development goals. Dr. Whittle suggested there's some things that geotechnical engineering societies cannot accommodate, but I'm here to tell you that what you do touches all of these, from economic development. If we have a successful protection of water in a canal, delivering water to a needful community, creating their economy, basically with that provided water, we are changing the world. We are changing the socioeconomic reality of that community. So all of these things, from quality education to gender equality to climate action, all of these things are very, very much upon all of us in all of our careers. And certainly the engineering community has a very major role to play in this. So in the same reports from the UN, building and construction together account for 36% of global final energy use and about 40% of energy-related carbon dioxide emissions when power generation is included. And significantly, the sustainable solutions for infrastructure development are needing to adopt innovative materials, new design, and new construction technologies to realize these sustainable solutions. So how do we adapt? Well, we adapt by considering the geosynthetic solution on every infrastructure project to ensure that the needs of the present are met, certainly, but without compromising our future together. So what are geosynthetics? Geosynthetics are synthetic polymeric formulated products to improve engineering performance of soil and rock. They've become an essential engineering material in transportation, geotech, geoenvironmental, hydraulic engineering. They're a subset, of course, of much larger recent developments of civil engineering materials, from composites to many other kinds of materials, new materials, superior materials to use in design. Geosynthetics are a big part of that community. There's worldwide annual consumption of about 6 billion square meters with a value and economy of about $5 billion. They're increasingly important in the context of our response to global warming and the urgent need for an appropriate engineering response. Now, there are literally thousands and thousands of polymers. The geosynthetics community is kind of a handful of those, right? Polyolefins, including polyethylenes and polypropylenes, do make up a very big component of the geosynthetics world, largely because of that carbon-carbon double bond in the molecular structure. Very durable, very resilient, very chemically resistant. The same plastic that we don't want to be around forever. In geosynthetics, we're counting on that multi-century service life that's so effective in creating our resilient infrastructure. We also use PVC, the same PVC that is used in a PVC pipe in your kitchen sink, underneath your kitchen sink. With a little bit of plasticizer, we can turn that same PVC into flexible PVC or barrier material. Polyesters, high tenacity. Polyesters are used in tires. They're also used in geosynthetic reinforcement products. Polyesters mobilize that high tenacity with very little strain. We also can use polyester in a recycled way. Polyester lends itself well to breaking all the way down and building back up. A polyester recycled community is being used to create non-woven filters and cushion geotextiles all around the world. We use polystyrene for fill. We use chlorosulfonated polyethylene and a few others, but a lot of polymer technology is focused on a relatively small community of these formulated polymers. Geotextiles are the workhorse of the geosynthetic community. They're filters, they're high-strength reinforcement, they're drainage. They're made out of a number of different manufacturing technologies, needle punching and weaving, knitting. Geogrids are made basically to carry load, to shed load upon. They are planar in their structure and they're high strength and high tensile modulus materials. We have geomembranes and geosynthetic clay liners, clay carpets, if you will, with high quality clay sandwiched between geotextiles. These materials are always used as barriers not only the liquid transfer, but also gas transfer, methane barriers, radon barriers, liquid barriers that we try to keep the contaminated liquid away from the clean, preserved liquid. We also have three-dimensional matrices, geonets, geomeshes that provide planar drainage. These are parallel sets of polymeric ribs that are joined together in a number of technologies, manufacturing technologies. Primary design is almost always hydraulic. Erosion control materials can be made 100% synthetic to reinforce a root structure, that vegetation that's so important. Can we get that vegetation to withstand higher hydraulic stresses if we wrap their root structure around a permanent three-dimensional structure to give it more resilient service life as a vegetation? We can also combine a temporary polymeric product with a natural fill to create a temporary product. So everything from temporary product to hard armor in erosion protection. And again, these geosynthetics and their product forms provide all of these primary functions. Many of them create composites where there may be a primary function, but there are often more than one secondary function. So filtration, drainage, reinforcement, separation, erosion control, barriers, protection, stabilization, stiffening, stabilization of roadways to increase their service life, and certainly stress relief. Very powerful family of products. And here's just some of the applications where railway ballasts are on a foundation of stabilized, consistently stabilized base, right? The same idea in a roadway where we're entrapping that aggregate, we're preventing it from moving and making it resilient to moisture, migration, keeping that aggregate there to prevent rut development. We can make a geosynthetic reinforced soil structure as a bridge abutment. One of the major advantages here is the speed of production. Immediately upon completion, we can load that structure so there's not a curing time or a reinforced concrete element. We also have designed strain in our design, so this makes it very popular for seismic areas and seismic design. Coastal protection, Dr. Whittle did a wonderful job of talking about the loss of land and the reclaiming of land or the protection of shoreline. And these big, large geotextile structures, geotubes that we can fill with local, regional material to create that land barrier, to prevent a berm that's protected against wave action, not only placed along the sea wall, but also out in the ocean to prevent, to lessen the energy as the water approaches the beachhead. More applications, landfill. Landfills all over the world really are now relying on the composite lining system, where geosynthetics play a role in reducing the hydraulic head that's active on the primary barrier. Thus, if there's a leak or there's some problem, the hydraulic energy that's active on that leak is infinitesimally small, given intimate contact in this composite lining structure. This is also the case in hydraulic dams, in tunnels. We're lining that tunnel. Immediately behind that lining, there's a drain, a geosynthetic drain quite often, that's taking away water before it can damage that tunnel. Gases that develop get vented off. Canals, infiltration of this precious water is no longer reasonably accepted. So we will create, again, a composite lining system, a liner to protect that water and protecting the environment in in mining waste and mining pregnant solutions and in cooling water. So in all of these ways, geosynthetics now are creating a sustainable benefit to our design. So we're replacing and reducing other construction materials. We're protecting limited resources. We're reducing the number of trucks that go to a site, the energy consumption, the associated CO2 hit, the emissions. We preserve the surface and groundwater, safeguard it from contamination. We're providing environmental protection and resilience, and we're providing economic growth and social welfare. And a couple of examples of that, here we are, instead of a 1 meter, 3 foot wide clay liner at the bottom of a landfill, we can bring 1 truck of a geosynthetic clay liner and reduce this entire carbon emission and install a superior low perm material with our montmorillonite clay blanket, GCL, faster and a more economical construction. Instead of a conventional retaining wall, we can use geosynthetic reinforcement to create a layered, resilient, flexible structure, and quite often a green structure with facing that incorporates vegetation. Here in geocomposite, at the bottom of landfills, collecting that rainwater and removing it for treatment after it becomes leachate. Instead of a very, very thick layer of drainage, we can use a geocomposite, thus saving all of this aggregate. The same themes in roadways, where the base course can be reduced as a function of reinforcement. Here, a drain is able to reduce the aggregate used for drainage in a very critical application of a landfill. And then we talked about this geosynthetic montmorillonite clay liner at the bottom of a landfill can replace a very thick, compacted clay liner. Lots of equipment, lots of low perm tests to prove it out. These geosynthetic clay liners are very powerful. Here is just a few pictures. This is a covered reservoir, not only protecting our precious water from infiltration, but also now covering this with a flexible geomembrane cover that's allowed to inflate and deflate based on water level to protect it from evaporation. Solar cells on an EPDM landfill cap in the US, with energy production being sold back to that local community that owns this landfill. So a lot of different resilient, sustainable applications of geosynthetics. The Geosynthetic Society sustainability page has a sustainability committee that operates that page. And we've been putting out through social media the Did You Know column. And each statement is backed up with a technical brief on how this is accomplished, what kind of design considerations. And behind this technical note, of course, there are many other resources and short courses to enable one to learn more about the successful use of geosynthetics. So the fundamentals of geosynthetics were introduced. Lots of products are available to solve a wide range of problems, demonstrated, articulated by Dr. Whittle, and certainly seen here, not only cost-effective, but sustainable, resilient solutions and critical for modern civil engineering projects. Further developments of geosynthetic projects and products continue and provide a lot of innovative solutions for what's ahead of us as a design engineering community. And with that, thank you very much. It's a pleasure to be part of this group, and thank you for your attention.
Thank you very much, Sam. It was a great presentation, very insightful, and I think you have presented very good resources for a lot of our colleagues who are participating right now. So now I may introduce our next speaker. Christopher Stevens. Hello, Christopher. Christopher I will talk a little bit about you presenting your background. So Chris has degrees in geology and geophysics with a specialization in permafrost and ground ice, periglacial geomorphology, thermal design and analysis, and numerical thermal modeling. Prior to joining SRK, Chris held a National Science and Engineering Research Council position with the Geological Survey of Canada. He also has worked on terrestrial and subsea permafrost related to mining, oil and gas, and transportation infrastructure projects in the USA, Canada, Russia, and Greenland. He has a very wide experience dealing with permafrost, which, as we've seen in the first presentation, is becoming every time more relevant. One important remark I want to give here right now is working at SRK, which is also a corporate associate in the International Society of Mechanical Engineering. So please, Christopher, the stage is all yours.
Okay, thank you, Mario. Can you hear me and see my title slide okay?
Clearly.
Great, thank you. And yeah, it's a real pleasure to have this opportunity today to share a little bit information with all of you about permafrost and infrastructure. And the title of the presentation, of course, here, rethinking our approach to permafrost and infrastructure for the next 40 years. I think we're at a real pivotal point in this field to make some real changes in the context of climate change and some of the challenges that we're facing today and into the near future. I'll start off this presentation, give you a bit of background on permafrost and some of the unique properties, because I understand that not everybody is aware or works day in, day out with permafrost and infrastructure in these types of settings. Then a little bit of information on some of the climate-driven changes to permafrost and the related impacts that we're observing in these regions, followed by progress that's being made in the field with adaptation of infrastructure to climate change and some new approaches and thinking that's going on. And then what the next 40 years might hold for us and some opinions on the directions that I think we need to be moving towards. So permafrost, it's soil and rock, ice, even organic material that remains at or below 0 degrees Celsius or 32 Fahrenheit for at least 2 consecutive years, including the intervening thawing season. So that's the technical definition of permafrost. Really 2 parts it boils down to. First, it's thermally defined and there's a thermal criteria that the material must meet. And then secondly, there's a time constraint that thermal criteria must occur over at least 2 or more years. So as I said, permafrost is thermally defined. And then the other point here to make is that not all permafrost is frozen. So we can have overburden pressures and loading and confining pressures, dissolved ions in solution and fluids that are in soil and rock that depresses the freezing point and actually results in material that's completely unfrozen yet meets the thermal definition. Typically, we characterize and map and estimate permafrost by its distribution of the area of land that's underlain by permafrost. So this map on the right-hand side of the slide, it's a northern hemisphere polar view looking from the North Pole down. And it's our estimate for at least this region of what permafrost distribution might look like. And of course, over time with climate change, this picture is expected to change. We have permafrost in low-lying, lowland environments. We have mountain permafrost in alpine settings, as well as subsea permafrost, so offshore beneath the marine environment. One of the unique aspects of permafrost that we have to address, of course, and makes for some very unique geotechnical properties of foundations that we're building on, is ground ice. So there's ice that forms in situ in the ground over time. And this picture on this slide is showing you some interbedded silts and clays, and you can see this segregated lens of ice that would have formed under thermal gradients that induced pressure gradients, negative cryosuction, negative pressures that allowed for migration of water up to and behind a freezing front. And then over time, it's accumulated this lens of ice. Ice comes in different forms, massive ground ice that may the bulk material could be 90% or more pure ice, mineral material and organics making up the other portion. You can have wedges of ice in the ground from thermal contraction, so rapid decreases in ground surface temperature that result in cracking of the ground, snow and meltwater infiltrating into that crack and refreezing over hundreds to thousands of years. Permafrost soils can also be ice poor with very little bonding of the mineral material at all. So quite a wide range of properties and foundation conditions that spatially and temporally vary that make for real challenges in designing, constructing, and operating infrastructure in this type of environment. Of course, for a long time now, we've known that climate-driven changes are taking place, and permafrost is responding to those changes. The graph on the right-hand side is showing you ground temperature measurements made at one location from 1997 to 2020. And you can see there's a progression of warming of the ground at this site. Other locations, we're seeing deepening of the active layer, the uppermost zone of soil and bedrock that seasonally freezes and thaws. That's deepening over time. In some areas, there's no longer complete freeze back of that active layer, and permafrost is thawing both vertically and laterally. Well, all of these changes, whether it's complete thaw of that material or just warming of it, is modifying geotechnical properties of the soil and rock that we're constructing infrastructure on. We know there's also feedback processes that are accelerating thaw in the ground, and that the landscape is not responding in a linear fashion. So differential response of the landscape makes linear infrastructure, pipelines, and roads very challenging to design for, construct for, and consider climate change into the future. And then the last point here I wanted to make on this slide was that permafrost degradation is contributing to environmental change. So it goes beyond just infrastructure, but there is natural changes to permafrost in these regions, such as the image at the bottom of this slide showing the run out of thawed sediments that are impacting things such as rivers, the sediment load in those rivers, and even the chemistry of the water, which impacts potentially aquatic ecosystems. Well, there's a lot of critical infrastructure that we've already constructed in these regions and areas where there is permafrost soils and bedrock present. I kind of consider any infrastructure that's critical being that has essential, it's really essential to our daily operations, maybe resource development projects. It could also be infrastructure that's supporting communities and our safety, as well as protection to the environment. And a lot of the infrastructure that's currently built and will be built in the future, it's in our very remote locations. It's highly costly to construct, to maintain, and to repair should there be adverse effects due to climate change and or failure of that infrastructure. And little redundancies built in. So you can see the bottom of this slide, some transportation infrastructure in the form of highways. These are often the only roads in and out of a location. There's not a road network, a series of roads that have been built in these areas. So if failure occurs, there's often disruptions to that network. Transportation infrastructure can extend to airstrips, port facilities. We're also, there's present infrastructure in the form of water retention structures, berms that are part of these water retention structures, and dams that are founded on permafrost. And then cases where waste has been and is currently contained, and it's reliant on frozen ground to maintain that containment. Well, frozen soil and bedrock is actually a really useful foundation to build on, to construct on. It's only when that material starts to warm and then thaws that we have larger geotechnical implications. And if we just look at these two series of photographs, these are of a frozen soil core on the left and the thawed material resulting from that on the right. When we transition across, if there is ground ice, that there is a change in the volume of the soil as we melt that ice and change from a solid state to a liquid. There's also changes, of course, in the mechanical and hydraulic properties of that soil. But one point I did want to make today was that the geotechnical properties are temperature dependent, and that means that prior to reaching the material's thawed state, as shown in this right-hand image, there are very dynamic changes, geotechnical changes in the material. Next series of slides are going to show you a few examples of what some of these impacts to infrastructure look like currently. Moving from left to right on this slide, you can see on the left side image, highway embankment. There's some failure occurring in the side slope that will eventually propagate, if not mitigated, towards the center line of the highway. This is due to perpetual thaw of ice-rich permafrost in the foundation. The right-hand image is showing you differential settlement of adfreeze piles that are supporting a pipeline rack right now. The bearing strength of those piles to carry that load is reliant on frozen soil surrounding it. And with warming ground temperatures and deepening of the active layer, those piles are losing their strength. These impacts extend to water conveyance structures. On the left image, a culvert that's been impacted and now is no longer functioning, resulting in impounding water against an embankment. That is also inducing heat into the ground and accelerating thaw of permafrost. And if that water starts to seep through this embankment or into the foundation, there'll be even additional acceleration of the thaw of permafrost and impacts to the infrastructure. The center image showing you some unfortunate dam failures that have occurred, and also rapid development of voids due to thermal erosion. I wanted to highlight thermal erosion because it's a pretty unique process. It's the combined thermal and mechanical erosion of permafrost soils, especially where we have ice-rich permafrost or massive ground ice. You can see from the series of images, field images shown on this slide, we have concentrated water that's flowing across the tundra, and it's finding its way in through a disturbance into the ground. And over time, the flow of water is advecting heat and contributing to both thermal and mechanical erosion. And here's a short video clip, and I'm hoping that everyone can see this, but there's flowing water. It's going into a void that is developing in the ground. That shiny mass is a massive ground ice that's being eroded. Here's another body of massive ground ice, and you can see the water flowing, creating this void. So quite a hazard. The water is not only impacting infrastructure and eroding this material, but with this comes often high turbidity water and water that has poor water chemistry due to its interaction with these permafrost soils that it's eroding, which is of concern if it reaches a receiving water body. Frozen soil creep, another geotechnical property and condition and process, time-dependent deformation of permafrost soils and ice due to stress applied. And the animation on the right-hand side of this slide is showing you a series of synthetic aperture radar images from a satellite that were analyzed and processed by 3V Geomatics. And over time, what you're looking at is the build out of a mine waste dump onto ice and warm ice-rich permafrost soils. And you can see that dump of waste rock deforming and moving, displacing down gradient. There's not only issues with stability of that piece of structure or facility, but also it's impacting other structures down gradient. You can see the building being plowed into. Well, we're starting to rethink our approach to permafrost and our design approaches that we currently use. Commonly, it's not the only design approach, but one of the more popular approaches is to maintain a frozen foundation. However, in a lot of areas, this is currently impractical, and we know towards the future, as we see changes in climate and increases in air temperature, we'll have similar challenges trying to maintain these frozen foundations. So this is a study that of pre-thawing the foundation prior to construction that we looked at with our partners from Transport Canada. Here we're looking at an approach of thawing the foundation to a target depth prior to construction, either using passive or active thawing techniques. A passive technique would be modifying the surface energy balance and letting more heat from the atmosphere going into the ground to induce thaw, or implementing active thawing techniques that rely on auxiliary energy sources to induce more heat into the ground. But we would have to be doing this in a controlled way, obviously, and to a target depth, removing that ground ice from the foundation, and then likely secondary work done to improve the foundation soils prior to construction. There's also adaptation of existing infrastructure that's underway to address climate change. And this is an example of a project in the Yukon, a highway section where sloped thermal siphons have been installed. It's a site where there's massive ground ice beneath the highway embankment. We know that that type of material is currently susceptible to the thermal forcing from the infrastructure, and it will continue to be a risk due to climate change going forward into the future. So we've installed what are called thermal siphons. They're closed pipes, as you can see in the image on the right-hand side of the slide. Those pipes extend into the ground beneath the road embankment. They're a closed system pipe. It's charged with a working fluid that's under a pressure such that when the air temperature is cold in the winter, colder relative to the ground temperature, that working fluid that the pipe is charged with will change from a liquid to a gas. The gas will migrate up to the surface where it's cooled by the cold atmospheric conditions. The gas changes back to a liquid state, releasing latent heat from the ground. And that cycle continues throughout the course of a winter and very effectively pulls heat from the ground. We're also leveraging progress that's being made in material science and looking at, are there other innovative construction materials that can be built into existing designs or future designs? An example is the use of phase change materials. Phase change materials are materials with a high latent heat of fusion. Probably the most common phase change or PCM material is water, which has a high latent heat of fusion when it changes from liquid state to a solid state of ice. In this case, the PCMs are manufactured and some are biodegradable and certified as being environmentally safe. With this, we're looking at the concept of integrating PCMs into our construction material and using them to seasonally store energy higher up into the infrastructure, mitigating heat transfer further down into the underlying foundation and limiting propagation of thaw over time. So where do I see the next 40 years? I think it's pretty widely accepted at this point that we are experiencing climate-driven changes to permafrost, and we're seeing the landscape respond. We're also seeing greater thermal forcing as a result and impacts to our infrastructure and its foundation. Predicted is that there will be continuation and increasing impacts to the infrastructure that we have now and the infrastructure that will be constructed into the future. It's going to increase operations and maintenance costs and potentially risk to users if not adequately addressed. I hope to last few slides there we're able to highlight some of the progress that's being made, but obviously more is definitely needed. I think one of our key things that we need to be doing to address some of these challenges, adopting a more proactive approach. So a proactive approach in this context really involves developing short-term goals that follow actions to achieve a long-term strategy. I think through doing that, we can lower mitigation costs of upcoming issues and reduce the scope of some of these challenges. And it's really doing the right things at the right time and not always being reactive, which often leads to higher cost and risk to infrastructure. I think the field of geotechnics, they're starting to do this in the world of permafrost and infrastructure, but we need to continue to be leveraging technology, both in geotechnical characterization of permafrost in lab and field settings, new ways to map permafrost and ground ice, and improvement in infrastructure performance monitoring for decision making, not only to identify where mitigation is required, to understand better what the geotechnical properties are beneath and surrounding the infrastructure, but also to make informed decisions and improve our designs going forward. There's also several groups that are leading the way in using technology as for surveillance and early warning systems. And then rethinking our approach to permafrost and infrastructure. As I highlighted, there's some efforts underway to develop alternative thermal designs. I think we need to make more considerations in the geotechnical properties of the material prior to reaching the thawing state. So there's a lot of room for development in that area. And then building that into some of our designs and adaptation to climate change. Also, improvement in how we consider climate change, our predictions, understanding how that material is going to respond over both time and space, and implementing that into the design work. And then lastly, I think this comment might apply to a lot of different industries, but definitely ours, is that the realization, we have to have that realization that multiple solutions and approaches will be needed for the next 40 years. And that really getting to improvements are going to be as a result of challenging conventional thought. I see geotechnics and as being a large part of us succeeding in the future in the area of permafrost and infrastructure. And thank you for the opportunity to speak today, and feel free to reach me by email if you have any questions or you'd like to discuss any of these topics. Thank you.
Thank you very much, Christopher. Your presentation was very illustrative. I think everybody here can agree, and I like very much your last messages about challenging the conventional thought and being proactive towards what's coming to us. So thank you very much. Now I will present Robert Maliva, who will be our next speaker. Hello, Robert. How are you?
Doing fine. Do you hear me good?
I hear you well.
Great.
Robert, he's a principal hydrogeologist with WSP in Fort Myers, Florida. He has devoted much of his 30 years career to international research and consulting for groundwater resources management, subsurface geology, and fluid flow investigation. His work includes analysis, design, and permitting of aquifer storage and recovery, and managed aquifer recharge systems, injection well designs, production well field design, and water resources evaluations. Just a little brief here. I introduce you to Robert. Please, Robert, the stage is all yours now.
Okay. We're going to move from the Arctic to the tropics here. And the topic of my presentation today is climate change and groundwater, focusing on Florida. And Florida, we're the lowest elevation, flattest state in the United States, which makes us particularly vulnerable to sea level rise. The figures on the right are some diagrams prepared by NASA showing the areas that are going to be inundated with a 5 and 10 meter sea level rise, which eventually is going to have a catastrophic impact on the state. The one good news is that it's not going to, this magnitude sea level rise isn't going to happen for at least another couple centuries. Excuse me. A lot can happen over 40 years. And a really great example of this is the Cape Romano Dome House, which is located in Southwest Florida, not too far from where I live, near Marco Island. On the top is this really innovative designed home that was constructed in the early 1980s using poured concrete. And on the bottom is what it looks like today. It's just sitting out in the middle of the bay there. So again, coastal areas can be very dynamic, to say the least. And the next generation of engineers are going to face with the challenges of designing for a much more rapidly changing world. as well as adapting existing infrastructure for new conditions. And low-lying areas, such as Florida, are going to be particularly vulnerable to the impacts of sea level rise, and also perhaps increased frequency and intensity of storms, hurricanes, and typhoons. And the impacts of sea level rise is going to include direct inundation, more frequent flooding, temporary inundation, accelerated coastal erosion, salinization of aquifers, and rising water tables or groundwater inundation. Now, again, I know that we're again, a very low elevation state, and there's some diagrams just showing the areas that would be inundated with modest rise in sea levels. So again, if we go to 0 to 4 feet, or up to maybe about 1.2 meters or so, the area of Florida, percentage that is going to be inundated will be relatively small, but it's going to impact obviously the low-lying coastal areas, and that just happens to be where most of the people live. So again, we're going to be facing over the next 20, 30, 40 years some significant challenges accommodating rising sea levels. Now, I want to just briefly talk about the impacts of climate change on our groundwater resources. Our state is highly dependent on fresh groundwater for potable use. Warmer climate is going to lead to increased water demands. But if we look at some of the climate change projections, and this is some diagrams from the IPCC fifth assessment report, and this is for the sort of the worst case RCP 8.5 scenario, you can see that the changes in precipitation is going to be quite modest, depending on whether 25 or 75 percentile range of the model ensemble. We're in a -10 to +10% range, so it's not going to be a huge effect. But the issue that we're facing is that our population is exploding. Over the next, I guess, 25, 40 years, we're expected to go from 21 million to 26 million people. So we're going to have a huge demand on water resources. Fortunately, the state is becoming more resilient. Out of necessity, we're developing alternative water sources, and things like groundwater desalination, and these tend to be more climate resilient, and certainly wastewater reuse is a big issue. What is sea level? What kind of sea level rise are we expecting? Well, again, looking at the most recent IPCC reports, the current rate of rise of global mean sea level is about 3.6 millimeters per year, which on a year-to-year basis doesn't seem like much, but it's accelerating. And then when you sort of add it up over the next 40 years, we could be looking at a 0.5 to 1 meter rise, which would have severe impact on low-lying areas. And again, in addition to increased just a direct inundation, with a higher sea level, it's a higher base or platform for storm surges and king tides. And again, some projections for Southeast Florida, the Miami-Dade County area. There's a regional sort of stakeholder scientist partnership group, the Southeast Florida Regional Climate Change Compact, and they have their sea level rise ad hoc work group, which is kind of a mouthful, but just show some of the projected relative sea level rises in the area. And again, looking at, say, 50 years, 21 inches, that'd be, over half a meter. Again, that's going to be an enormous impact on coastal areas. Some of the other projections are even more shocking. I think they're a little bit excessive, but again, to turn of the century, if you're looking at a meter or two of sea level rise, where a lot of the areas, that's elevations no more than several meters, it's going to be an enormous challenge for communities. Again, looking from a biological perspective, we're going to see profound ecosystem changes, permanent and temporary flooding of low-lying areas. These are some diagrams prepared for the Everglades National Park, prepared by the Park Service, again, showing the areas that are going to be inundated at various times in the future. The top is sort of the median 50 percentile projections. The bottom is an extreme 99% percentile. But again, this is sort of a very biologically sensitive area. And again, the level of sea level rise is going to be much greater than any of the ecosystems can accommodate. A really useful tool in the United States is the NOAA Sea Level Rise Viewer, which is it covers the entire country, the coastal areas, and it has zoom features, so you can again zoom in on your local areas. It has aerial photographs as base maps, and you can look at what areas are going to be inundated for various sea level rises, and then it shows the areas shown in blue or shades of blue are the areas that are going to be inundated for a 2-foot sea level rise. It's about, I guess, 0.6 meters. And again, all the critical coastal ecosystems are going to be again basically totally inundated. Most of the developed areas are not going to be inundated because they're built up. The area of Cape Coral here, the pad levels of the houses is about 5 feet. But as sea level rises a couple feet, everything's going to be on a higher base level, much more frequent flooding. And as it gets beyond that, you're really running into the habitability area of some of these low-lying areas. Now, one of the, looking at, from perhaps from a more geotechnical perspective, one of the aspects of sea level rise that really hasn't received as much attention, but really needs to, its effect on the local coastal water tables. As sea level rises, shown here by the dashed line, the water table in coastal areas also is going to rise. And this can result in a permanent inundation of low-lying areas, as well as temporary inundation during high tides or rainy periods. And this can cause really a slew of problems. Again, you can get local inundation, soil waterlogging, which can be a big factor impacting, say, the integrity of foundations, flooding of buried infrastructure, flooding of roads, both permanently and temporary. And it can also can compromise the performance of drainage and septic systems that are gravity driven. And again, temporary flooding is going to be a big issue. Again, as sea level rises, the water table is going to rise. We may even see more intense rainfall events. Storm surges and king tides are going to occur on a higher sea level baseline. And, one problem, as the water table rises, you have a thinner unsaturated zone. So there's going to be lesser soil storage capacity during rainy periods. So again, much more of the rainfall, rather than infiltrating, is going to be running off and flooding low-lying areas. And the highest sea levels would be expected to impair the performance of gravity-driven drainage systems, as well as also some gravity sewage systems. So a lot of these are going to have to be upgraded to pump system, and drainage systems are going to have to be installed in a lot more areas, but particularly, obviously the low-lying areas. How do we go about looking at these issues? Normally we think in terms of workflows, and for groundwater inundation mapping, normally you need to start off with some projection of global sea level rise at some time in the future. Really, that depends upon your study goals. How far out in the future are you interested in it? 40, 50, 60 years? Usually we will get this information from published studies, some of the IPCC reports or some of the modeling databases. Global sea level rise is important, but more critical is the relative or local sea level rise, which also includes the rate of land subsidence. And normally we can get that rate from some of the empirical data on the historical relative sea level rise. Next, we need to determine what the future water table elevations is going to be in the coastal areas. And there's several ways of looking at that. A very simple way is sort of a flat water table estimation method, where we just take the current mean high water level in an area and just add the relative sea level rise. If we have a water table surface map or potentiometric surface map, we can just add the relative sea level rise to that to get the future map. Or this can be done with groundwater modeling with the relative sea level rise simulated as a boundary condition. Another data source that we need is a high resolution local topographic map These are typically digital elevation maps, DEMs obtained through LiDAR. And then you calculate, the depth of groundwater by simply subtracting your local land surface elevation from the water table elevation, using a GIS framework. And once this is done, we'll get a depth of groundwater map, and then we need to look at all the different infrastructure in the area of concern and look at how it can be impacted, and then look at what are our options for addressing those impacts, as well as coming up some time frame in which action is going to be needed. And I mentioned, the impacts of both sea level rise and groundwater inundation in coastal areas really is going to be extreme in some areas. This is a study that was done in Honolulu, Hawaii, where it looked at combination of direct and groundwater inundation for a 0.98 meter sea level rise. On the left is the current areas that may experience flooding or a shallow water table that is less than 0.33 meters, less than a foot depth to water. And you can see if we have this 0.98 meter rise, a huge area is going to be impacted, both direct inundation as well as having a very shallow water table, with waterlogging of soils and all the other associated impacts. And again, the area that's going to be impacted by groundwater inundation may be significantly greater than the area that will be directly inundated. And I mentioned septic systems. This was a study that was done in Miami-Dade County, Florida. Again, septic systems to operate effectively, there needs to be an unsaturated zone below the drain field to allow for some of the biological contaminant attenuation processes to occur. On the left is a diagram with the yellow and orange dots showing the locations of septic systems that are vulnerable under current conditions. On the right is a map of those systems that are going to be were determined to be vulnerable out in the year 2040, which again, this is less than 20 years from now, much less, a 40-year time frame. And the estimate is to hook up all these systems to the municipal sewer system. I believe that was about $8 billion, and that's B with a billion, and that was done several years ago, so it's undoubtedly higher. So again, it's just a small example of the liabilities that sea level rise may occur. And again, this is groundwater inundation. This is not even dealing with the direct inundation that's going to impact some of the more coastal areas. So, a question that arises is, what's, if you're somebody entering the field, what skills and knowledge with respect to climate change are you going to need or should have? And I think the key point is that climate change evaluations are inherently multidisciplinary team efforts. You're not expected to be able to know everything or do everything, but team members really need to have an understanding of the basic issues related to climate change, so you can, contribute to the effort, at least on a working or conceptual level. And some of the things that, people entering the field really should have a firm knowledge of is just the climate change basics, as well as some of the latest projections. It's important to understand, that our projections are going to depend upon, what the future climate is going to look like, depends on the future emission scenarios, which are still to be determined. There's understanding of just what a general circulation model is and how they're used to project the future. There's things like downscaling, incorporation of climate change into hydrologic models. There's some of the data sources. Most people have heard of the Intergovernmental Panel on Climate Change, but when we're looking at actually modeling data projections, the coupled model intercomparison project databases can be very useful. You really need to have a knowledge of what climate change likely may occur, as well as the sea level rise projections in your work areas. And it's useful just to have an understanding of how the different methodologies that are used to evaluate the impact of climate on groundwater and surface water levels and availability. And I'm happy to answer any questions.
Well, thank you, Bob. That was very fascinating, and thank you for bringing us back to warmer climate. So now we have, so Ash, are you on?
I am. I was temporarily booted off, but I managed to get back on. Cool. Our next speaker for the seminar is Jan Quebec. Jan, you there? Just do a quick sound check and then I'll introduce you.
Yes. Can you hear me all?
Cool. We can. Fantastic. Thanks very much for joining us. Dr. Jan Quebec. Jan's a principal and geotechnical engineer at Oricon here in New Zealand and also a global company. He's been a geotechnical engineer for about 15 years and lives in Christchurch in New Zealand. What a fantastic place to be when the ground's not shaking anyway. He's a geotechnical and earthquake engineering specialist, and outside of work, he is also involved in the New Zealand Fire and Emergency Urban Search and Rescue Crew in the Southern Team. Also very, very interesting. As a geotechnical specialist, he is very closely involved with the Canterbury earthquake sequences, Japan tsunami response in 2011, Nepal 2015, and most recently Kaikoura in 2016. Jan's worked as a first responder and engineering specialist, all overseeing various aspects of the recovery. Since 2011, he was seconded to the New Zealand central government as a chief geotechnical engineer for the Canterbury Earthquake Recovery Authority, and later to the Land Information New Zealand team. Over the past decade, he has managed severely earthquake damaged buildings and land. Jan is a leader in the digital innovation and the application of smart technologies in the geotechnical space. Jan enjoys peer reviews, expert witness work, forensic engineering, and champions technical mastery. In his past career, Jan was a university lecturer and academic. He authored over 70 technical publications on various aspects of civil and geotechnical engineering. His passion and main doctorate research background is on the sustainable application of smart materials and technologies for horizontal infrastructure, civil structures, and buildings. He often speaks at international conferences on innovation, resilience, and state-of-the-art engineering. So hopefully you can bring plenty of that flavor to your presentation today, Jan. The floor is all yours when you're good and ready. Thanks for joining us.
Thank you. Thank you, Ash, for the kind introduction. Tēnā koutou, everybody. A traditional greeting. I have only 5 slides and I actually wanted to have more an engagement, a discussion with the audience. But can I have the next slide, please? And I'm going to talk about sustainability and climate change. But before I go on, I just want to make the difference clear how I see sustainability and climate change. Climate change is a man-made effect that we have created as a species over the past 150, 200 years. Sustainability is an effect that we will have to continue pretty much ongoingly to maintain and manage our natural resources. And in both cases, we as engineering specialists, and especially geotechnical engineers, can manage and provide critical input. Reflecting on my own career, I've worked with many government organizations, private clients, and what I always take out of that is that sustainability and climate change means different things to individuals and different organizations. But as geotechnical engineers, we can actually bring a lot of the work that we have done on or normal day-to-day work to both climate change and sustainability to actually solve some of these wicked challenges we have. Can I have the next slide, please? And I'm just going to demonstrate to you how, because if you look as a geotechnical engineer, if you have a market view, then these are the markets we're pretty much continuously working with, whether education, water, 3 waters, the transport infrastructure, resources, manufacturing, the construction sector, data and telecommunications, such as large data centers, defense, national security. It doesn't actually matter. Geotechnical engineering is always at the core and the beginning of most of these projects. If you look at more a specialty view, please the next slide. And look more at where do we have our expertise. And as geotechnical engineers, again, we actually double in pretty much most of these specialties, whether it's road and transport networks, sports and entertainment stadia, tall buildings design, looking at the environmental planning, looking at large power generation and dams, general bridges, building designs, or even tunnels. And in the past hour and a half, we heard many examples of actually works and projects where geotechnical engineers have actually worked in. Can I have the last slide, please? And this is actually a picture I wanted to actually leave on there, because we have a responsibility, and I'm looking right now specifically at sustainability, to leave the place we're actually living in better for the next generation. Sustainability for me is actually working with the current resources and to make sure that we actually look after them. And this is custodianship that we actually need to take on and manage our resources to actually help our communities and economies to transition in a future that our kids and their kids have the same opportunities we have. I know that there were some questions from the audience that Lucy has brought together. And I just wanted to open it also to the audience. What does sustainability and climate change mean to you? How can we, as the panel over here, answer any questions that you might have and talk about projects and examples that we have used? Lucy, do you have some questions that were previously submitted? You're muted.
Okay, yeah. We do have a few questions that were previously submitted from the audience during registration. Although I think the audience would be very interested in hearing about your professional background. When we were talking, you have a very international background, which I think our audience can relate to.
So if you actually hear, the accent is quite funny, and probably you guessed that it's a mix of hodgepodge. I was born in Czech Republic, but I grew up in Germany and did a degree in mathematics and then civil engineering. I thought a more practical approach would be better than actually crunching numbers. I did a PhD in earthquake engineering and a master's in geosynthetics in Scotland, and then decided to travel the world and work with the United Nations for several years, seeing essentially how communities work. And I went to places from North Korea to Libya to Afghanistan to a lot of countries ending with Stan, and eventually ended up in New Zealand and founded the ground engineering division for Oricon over 16 years ago in New Zealand. And throughout my work, I started in 1995 looking at the earthquake damage in Kobe. And I looked how societies and communities are impacted by large natural disasters. And Kobe in 1995 made a tremendous impact on me. I was there about a year ago. A year after the event itself, and looked at the design of geosynthetic reinforced walls. And at that stage, it was quite interesting to see that structures that were never designed and intended to survive such large shaking essentially were undamaged, whereas traditional concrete structures standing next to it, essentially in the same vicinity of the area, were completely destroyed. And that triggered to some degree my master's and my PhD research, but also my passion over the last 20 years in disaster management. And I'm currently working as a contracted engineer with New Zealand's fire and emergency, and I'm one of the very few engineering specialists to the fire service over here. And essentially that means that if there's a natural disaster in New Zealand or overseas and we're being deployed, I'm providing the engineering expertise on slope stability, building collapse, tunnel collapses, and flooding, and helping to keep the team safe, but also enable a safer rescue of the people that are either buried in buildings or buried by landslides. And what I have seen is, again, reflected by the previous speakers, that the severity and the frequency of natural disasters appears to be increasing, but also not necessarily because of perceived indirect impact from climate change, but we have over the last 20 years put a lot more vulnerable infrastructure into places where there is a higher susceptibility that this infrastructure will be damaged. Looking at my own career and looking all the way back 20 years ago plus on COBA, what fascinated me were the retaining walls and the foundations. And I started to look into this in more detail and discovered the use of geosynthetics. Geogrids were mentioned by Sam previously, and looked how these could be actually used for foundations underneath it to create a block of soil or a mattress of soil that can help a building survive earthquake damage. And I've managed to create, design, and construct several of these structures before the Christchurch earthquake. And it turns out that that was very, very successful. It's now part of the Engineering New Zealand engineering guidance in New Zealand to use geogrids underneath shallow foundations to increase the seismic resilience. So that's some of the contributions that advanced engineering materials can do. And it's not necessarily that you increase the seismic resilience, because you can actually use either poorer geotechnical materials, or you can reduce the thickness of the foundation mattress. You're actually creating also a more sustainable approach to design. And as Sam mentioned, geogrid reinforcement is being used widely in seismically active area. It is, and it's now became an ever-increasing tool in New Zealand to reduce volumes of fill and strengthen the materials that we have.
Yeah, that's very interesting. And so speaking of earthquakes and Kobe, I was actually involved in a tsunami preventative measure in Indonesia. So I think we all know the Indonesia North Sumatra tsunami. And my project was actually looking into preparing the next community for a tsunami, and rescue efforts and planning and also raising earth to provide for these evacuation facilities. So I was wondering if you can talk a little bit about sort of these urban rescue efforts, and also what you can bring to the table as an engineer, like looking at these rescue efforts.
I'm going to be very, I'm going to take it around another way. And I'm going to start with a supermarket, a grocery shop, right? And usually say, you know, how is that relevant? Well, first of all, grocery shops, if you normally design them and put them into seismically susceptible land that's vulnerable to liquefaction, they can be damaged, right? But if you actually look at the grocery store, suddenly you have a community facility that actually provide a post-disaster functionality, but that's generally not recognized at all. So in Christchurch, we lost dozens of grocery stores. So suddenly people that were quite vulnerable had to travel long distances to actually obtain their food. But also rebuild was quite critical. How do we rebuild? Do we rebuild exactly the same thing over again and risking again that we get terminal damage to these structures, or can we actually do it much better? And that's where individuals can actually engage quite effectively. In my case, I engaged with my experience, seeing how these structures got damaged. And I believe that with a few more seconds of shaking during the 2011 earthquake, we would have had multiple structures collapsing. So the earthquake was only 12 seconds long, very, very brief. We're expecting shaking from the next event, which is the Alpine Fold, which is about 150 kilometers away from Christchurch, to last in the order of 3 to 4 minutes. So 12 seconds to 3 to 4 minutes, albeit slightly lower PGAs. It's a different kettle of fish. So we certainly didn't have our penultimate limit state event. So how can we prevent, when we rebuild these structures we're already damaged, to future-proof them? Because why would you want to build a structure over and over again? Despite the fact that you could use these structures and build them in the New Zealand Building Code and consent them, does it actually make sense? So speaking at the board level with the owners of these supermarkets or grocery stores, we said, like, for very little effort, you can actually put hardening or in these facilities, you can actually make them perform much better. In the longer term, that actually is a much more sustainable approach, because you treat the ground, you can have a standard structure on top of it from a geotechnic perspective, and you have a post-disaster functionality. Because what do you do after a large earthquake or a flooding? Well, you go out and buy rolls of toilet paper, apparently. That's what at least most people do in COVID, right? So these structures need to be able to function pretty much immediately afterwards. And not just kind of function as a one-off, but continue to work and function. So our design was completely turning it over, seeing how can we actually increase the resilience against seismic shaking of these structures. And the second thing, during construction, what could we actually do to reduce the carbon footprint of these structures? So instead of using ground improvement of 6,000 square meters, using stone columns, and especially in Canterbury, it's quite difficult to get fist-sized rocks that you generally would require in these stone columns, because we simply don't have any hard rock quarries over here. And the road gravel we have, if you break it down, you end up with particles that are small. So could we use something else? Yes, there's crushed concrete that we could use as a recycled material, and that it reduced thousands of cubic meters of material uptake. In other areas, we were able to use geogrids and poorer quality fill that would have otherwise gone to waste as a cover material for our landfill. That was able to be used fairly successfully. So as individuals, we have the ability to impact onto design, and we can do it at a governance level by talking, say, to a board of the owners of our structure, but also even larger projects. We can actually use our influence to talk to subject matter expert, our client organization, whether it's a road transport agency or whether it is a large railway association, say, look, if you actually relax or change your performance specification, you will still get a well-performing structure, but it is able to be done in a more sustainable manner and at actually often at a reduced cost. All right. Having then the ability to have structures that are much more resilient, we do not actually enter in the problem that these structures could be damaged in an earthquake and require people to be rescued from it.
Yeah, so I guess I think a lot of us practicing engineers, our duty first and foremost is to follow the code and do what we were paid to do, right? But I think
correct. But the code is the absolute bare bone minimum to get everybody out of jail. It is not the target. it is the bare bone minimum. That's how
Right.
you have to see it. What do you do? What do you do? And how do you use the smarts to actually then go beyond?
Well, I think what you're saying is that we have a responsibility as engineers and as subject field experts to influence the design such that they're more resilient on one hand to natural disasters, and then also to reduce carbon emissions where we can, and to still
Absolutely.
have safe structures.
Absolutely. And if you look at it, we are perfectly placed to do that, because we understand geomaterials very well as geotechnical engineers. We understand how these materials behave and how we can modify them in order to behave better or have other properties, how they can actually exhibit composite materials that otherwise they wouldn't have.
Yeah. Okay, well, we are running a little bit long on this session. Thank you everyone for staying on. Do you have any last remarks before we conclude the session?
No, thank you very much. I really enjoyed this session. It was very interesting.
Okay, thank you. Thank you so much. We just have a couple of concluding remarks, mostly just to thank all of our speakers and panelists for attending and staying on with us. Thank you everyone for attending live. I know a lot of people will be watching this recording because the timing didn't work out. Thank you everyone for attending, and to our speakers. Hope to see you all live in 3D in other sessions, maybe in Sydney.